Hello everyone! Today we're going to talk about IP addresses. So what is an IP address? Actually, we often see IP addresses, and it is essentially a way to identify a location within our network. For example, if our destination here is this IP5, then I need to check who exactly is this IP5. For instance, if you were trying to find someone globally without knowing their name, it would be extremely difficult to locate them in the vast sea of people. So what about IP addresses? They are used to identify nodes or interfaces within our network, and we assign each one an address, and this is used to forward data packets within our network. Now, if a user wants to connect a computer or a device to the internet within our network, they need to apply for an address for that device. This address is used to identify one of the nodes in our network and to locate the data's destination, enabling communication through this IP. So, why does everything need an IP address? Can we do without it? Actually, it can't work without it. It's similar to a locator, meaning it identifies where you are. For example, many of our applications now, they have an IP location that can indicate which location or city you are in, right? Some students might be in the United States, while others might be in Japan. If you post inappropriate comments online, and someone wants to track you down in the future, they would actually use the IP address. The IP value is something we configure on the network device interface, rather than the device itself having a specific IP address. So, if I have a router now, and on this router, I have many interfaces. Each interface needs at least one IP. It's important to note that the interfaces where we use IP are usually on our network devices, like some interfaces on our computers. So, what does an IP address look like here? In our enterprises, the most commonly used is still the IPv4 address, which is 32 bits. We can refer to previous packets. I don't know if everyone still remembers, but we mentioned that each line is from 0 to 31 bits. So actually, it's our 32 bits. Now, in this process, it uses a dotted decimal notation. What is dotted decimal notation? It means that there are 4 groups of numbers separated by dots. For example, what we see here, 192.168.10.1, is one of our IP addresses. In the future, when we see something like 1.1.1.1, this is also an IP value, all separated by dots. Now, in this context, we say, an IP address volume is equal to 32 bits. It is divided into 4 groups, meaning what does each group correspond to? Each group actually corresponds to 8 bits. So our actual index corresponds to 8 binary numbers. Now, what is decimal and what is binary? First, let's talk about decimal. When we usually talk about IP addresses, we say they are in dotted decimal notation. The so-called decimal system is this number. From 0 to 9, you cannot say that you can use a single digit to represent 10. It's impossible. We now universally recognize that 10 is represented as 10, and we must use 2 digits to express it. So here, this is our decimal system, meaning that every 10 requires moving 1 place forward. If we talk about the binary system, it advances by 1 every 2, meaning we can only have 1 or 0. In the entire binary system, you will not see the number 2. When we perform conversions in the future, it is essentially a decimal number corresponding to it. For an 8-bit binary system, how do we calculate it in the future? Well, we can use the table below to calculate. If you can't remember, it's okay. For example, here I only need to remember that the last digit is 2 to the power of 0, then it's 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 4, 5, 6, and 2 to the power of 7. When calculating, you just need to remember that the last digit is 1, and then multiply by 2 each time. For example, 1 multiplied by 2 equals 2. 2 multiplied by 2 equals 4, and 4 multiplied by 2 equals 8. 8 multiplied by 2 equals 16. 16 multiplied by 2 equals 32. 32 multiplied by 2 equals 64. And 64 multiplied by 2 equals 128. So in the future, if we want to calculate, how do we do it? You just need to calculate, and if I assume this is in binary, to convert to decimal, I just need to add up the numbers where there is a 1. For example, here I just need to calculate 128 plus 64, and the resulting number is 192. For instance, here it is 10,1,000. So how do we calculate it? I calculate 128 plus 32 plus what? Plus our 8. And these 3 numbers add up to 168. This means that for the positions where there is a 1, I extract that number and add them together. For the positions where there is a 0, I simply ignore them and don't consider them. In the future, when we calculate, if the first 4 digits are zeros, you treat those 4 numbers as if they don't exist. Here, this is a 1. Take this number, right? What? We take it out and say we don't look at the number 10, we don't look at this number. This means 8 plus 2 equals 10. And calculating like this is very simple. What? Of course, if we reverse it, let's say here, if we reverse it, and I only know this 11,000, how do I calculate a time index? At this point, everyone can imagine. Let's say you are a boss, and you need to buy gifts for your employees right away. Now, this is a building, and this building has a rule that you must buy these gifts in order. For example, you currently have $192 in your hand. If we want to convert this 192 into a binary number, we subtract these numbers from 192. First, you arrive at the first floor. Can you afford the $128 gift? You can, so you mark this position with a 1. Subtracting 128 from 192 leaves you with $64. With $64 remaining, we go to the second floor and take a look at this item. We mark 14 as 1, and then I can't afford it, so we end with 000. Now you can calculate how to convert this decimal number into binary. For example, let's take 10 as an example. I only have 10 yuan now, but I want to buy gifts for my employees in this building in order. Can I afford 128? I can't afford it. So here I mark it as 0. Can I afford the $64 one? I can't, so I mark it as 0. Can I afford the $32 one? I can't, so I mark it as 0. Can I afford the $16 one? I can't, so I mark it as 0. Can I afford the $8 one? Ah, I can afford it, so I mark it as 1, and we need to subtract 8. Wait, now you only have $2 left. With only $2 left, can you afford the $4 one? I can't afford it, so we mark it as 0. Can I afford the $2 one? I can't, so we mark it as 1. Finally, after spending this $2, do we have any money left? No money left. So here we can't afford the $1 item, and we mark it as 0. This way, we know how to make a conversion. Actually, when we talk about the decimal system, it means that what you usually see is designed to help us better use and configure the network. However, the devices can only support binary. So here, we need to be familiar with the conversion between decimal and binary. Now, let's look at the smallest digit here. If I don't represent each digit, meaning each digit is 0, and I don't assign a value to any of them. Now here we can calculate that if each digit is 0, it means I don't add any of the numbers. So here, if I have 8 zeros plus 1, it's still 0. Now for the second one, if it's also 8 zeros, well, it's also 0. So finally, if I say that my smallest number is 0.0.0.0, then conversely, if I say that my number is the largest number, each digit. I take each digit as 1, then that would be using our 128. Add 64, then add 32, 16, add our 8, 4, 2, and 1. When you sum them all up, you'll find that this number equals 255. So here, we say that such a set, what does a decimal correspond to? It corresponds to a binary number, which equals 250. There are a total of 4 sets of numbers, meaning each set's maximum is 255. So the range of an IP address is 0.0.0.0 to 255.255.255.255.255. Now, within this, our IP address is actually divided into 2 parts, the network part and the host part. What is the network part? The network part identifies the network I am in. Because if we didn't have the concept of a network, we wouldn't have the concept of a network. Okay. Now I'm telling you, the person you're looking for now, his name, hey, is Zhang San, and I don't tell you where he is, then how would you find him? You can't find him because you don't even know where he belongs. We have no way to find him effectively. So here, we divide it into different segments. For example, if they all start with 192, 168, 10, then in the future, when you look for him, you can search for the numbers starting with 192, 168, 10. and it will be easier to find him within this network segment. Now in this context, we say that an IP address, if it is part of our network, represents our network here. The IP address of the device belongs to a network, and if network devices have the same network address, we say they are on the same subnet. If we look further, what is the purpose of this host part? It identifies a host to distinguish it within our network. For example, if I want to find someone, let's say we enter a school and want to find a student, and you only know the student's name is Jack. How would you find him? You wouldn't be able to. But if you know he is in class 1 of grade 3, then you can look for him. Grade 3 is like his network, and class 1 is like his host position, meaning we can locate him more precisely. Here, by combining the network part and the host part, we get our IP address. So how do we distinguish which network it belongs to? How do we distinguish which grade it is? Continuing with our analogy, we need something called a subnet mask. The subnet mask actually looks very similar to an IP address in a format like 255.255.25.0. So we have a subnet mask. It is also 32 bits and is represented in dotted decimal format, just like an IP address. However, the network mask is not an IP value, and the network mask must be continuous. We say that such a series of ones and zeros is composed of continuous ones, which you cannot see in the instruction mask. 00 followed by 1111. It must always start with continuous ones. You cannot have continuous zeros first, nor can you have such a pattern. 101 or 0 in such a situation. This is impossible to occur. So we say this is a subnet mask, which is also represented in binary, but you can convert it into, generally speaking, when we want to calculate a subnet from a decimal system, we convert both our subnet mask and our IP address into binary. After converting to binary, the part of the IP value corresponding to the position where there is a 1 in the subnet mask. What is it? It is our network portion. For the network portion, I copy it exactly as it is, and for the host portion, I set everything to 0. Sati. At this point, I can calculate its subnet. Sat. For example, during this process, its subnet is. Is saying it like this too complicated? Then we can say its network is 192.168.110, and for the last digit, I say, if all the parts where the subnet mask is 0 have their corresponding IP values set to 0, ship. Then at this point, the 8 zeros are converted to decimal, which is 0. This way, it forms a subnet, and we can use this method to calculate the IP address combined with the subnet mask. Its subnet. In this way, we can say its subnet is 192.168.10.0. If I want to mention this address, and its subnet mask, how should I say it? We can say here 192.168.10.1 with a subnet mask of 255.255.2555.0. Writing it like this is too cumbersome. So we can say 192.168. 10.124, which is the so-called 24-bit subnet. You can understand it this way. 24 indicates how many ones there are, which is the slash number. Now in this case, this is 8 ones, this is 8 ones, and this is 8 ones. So here it's 3 times 8 equals 24, and here we can write 24. If it's 4R5s, at this point we need to write dot bolt 32 because each 2R55 actually equals 8 ones. This is our subnet mask. Now, during this process, we can use this IP address to identify a network segment, while the host part identifies the host. In other words, I'm just looking for this person. For example, now in this context, our number is on some street, and there's a person named John. Now, based on this location, which is a precise location, I can find him, and the earlier part indicates the city he is in. And the latter part is his precise address, meaning I find him specifically within the community. I'm only looking for this person. By combining these two, I can locate a unique device. Now, during this process, if we need a gateway here, Why do we need a gateway? In the network, everyone should remember a phrase. Within the same network, I can communicate directly, or within the same subnet, I can communicate directly. But for different subnets, I need to find a gateway. Yeah. What does this mean? For example, if you're at home now, and you want to have a glass of water while in your room, you just look around. The glass of water is in the same room as you, so you can pick it up and drink it. But what if the water is not in the same room as you? What do you do then? You would need to go through the door of your room to another room to find the glass of water. But if your room doesn't have a door, can you go out? You can't. So it's the same in this context. If I want to forward in the future, I can only communicate with those on the same network segment. If I want to communicate across different network segments, I need to find something. Find a gateway to help me forward and transmit. It receives and processes data packets from a host on the local network segment, and then forwards these packets to a destination network segment across different network segments. To achieve this function, first, we need to be on the same network segment as the gateway. If I can't find the gateway on the same network segment, there's no way I can use the gateway to find others. The gateway address is often an address on the device interface. For the convenience of IP management and network connection, IP addresses are actually divided into 5 major classes by an international organization called IANA. These 5 classes are categorized as A, B, C, D, and E. A is an international organization that allocates time to countries, which then allocate it to operators, and operators distribute it to us. Now, within this, the first thing we can use is actually these 3 types of addresses, A, B, and C. Among these A, B, and C types of addresses, one of the ranges is from 0.0.0.0 to 127.25.255.255. The B class is from 128.0.0.0 to 191.255.255.255. And the C class addresses range from 192.0.0.0 to 223.255.255.255. So when you remember this in the future, it's actually about this A class. The first bit must be 0. For a B class address, the first 2 bits must be 10. For a C class address, the first 3 bits must be 110. For a D class address, the first 4 bits must be 11 and 10. And for an E class address, the first 4 bits must be 1111. So, why can we only use the A, B, and C classes? Because these 3 classes are unicast addresses. Only these addresses can be assigned to our computers. Unicast is essentially one-to-one, meaning I can send it to you individually, and you can send it to me individually. A D-class address is our multicast address. What is a multicast address? A multicast address means, hey, I can send to many. Oh, of course, there's also a special address here, which is 25.2555.2255.2555, and this is also a one-to-many called broadcast. So, what is the difference between broadcast and multicast? I don't know if any of you have attended such a class. In computer classes, in China, there are such computer or information classes. If in the future you are going to attend a class, we might play on the computer for a while before class, because once class starts, our desktop becomes the teacher's computer desktop. In the earliest days, they actually used broadcasting. Broadcasting means that as long as one computer, ours, and the teacher's are connected to one device, the teacher's computer will send a broadcast. And this device will receive the broadcast. Then it will execute an action, which is to broadcast. In other words, as long as it is connected to the same device as me, I will send it over. No matter how many devices I am connected to, I will broadcast to them all, and all devices can receive it. But now, in the room, everyone knows there are cameras. If I receive something from the camera, is it beneficial to me? Not really, because the camera's configuration is not high to begin with, and if you send me a bunch of stuff, it becomes useless to me. It would make me, very laggy, which is definitely not acceptable. So here, later on, everyone felt that it was wasting our bandwidth and consuming our resources. Our hardware. What does it become? It becomes our homeland. The homeland can only be received by those in our group. If you're not in the group, you won't receive it. For example, many times people join groups, and only by joining the group can you know what they are discussing. Well, if you don't join the group, can you hear it? Can you receive it? You can't receive it. Well, and this is the difference between our host and broadcast. Now, our first type of address is the host. The host address cannot be configured on our devices. If this is hard to understand, you can think about it like this. When you're listening to some radio stations on a radio, can you say that you are the station? Not at all. I am just receiving things from him, so this address cannot be configured for our device. Besides this, there is also an alien address, which also cannot be configured because it is a reserved address used for research and military purposes, and we cannot use it. So this is our ABCDE, and actually we can only use ABC. Among them, Class A has a subnet mask of 8, Class B has a subnet mask of 16, and Class C has a subnet mask of 24. Now, if it's our Class A, let me help you think about how this subnet mask is converted. It is 205.0.0.0 for us. If we say 16 bits, we have two 255s, one 255 equals 8, and two 255s equals 16, 0.0. As for Class C, it is three 255s. Now within this is its subnet. If during this process, as I mentioned earlier, our IP addresses of Class A, B, and C are the only ones that can be used, but not all addresses within these three classes, E, are usable. For example, we have an address, 192.168.1.1. Actually, according to what was mentioned earlier, we can say it is a Class C address. However, when we talk about the network segment it belongs to, how do we calculate it in the future? Isn't it based on its subnet mask? For example, if it's 3.255.0, we calculate its network segment. What network segment does it belong to? It belongs to a network segment, where the first three groups of numbers, as long as they are 255, correspond to 8 ones in binary, which means the IP is fixed. So if you encounter this situation, you can remember that. If you come across a subnet mask with only 255 and 0, you can remember that the numbers corresponding to 255 are fixed, which means 192. 168.1, and what about the number corresponding to 0? It's arbitrary, whatever you want it to be. In this case, it can be 0, with the minimum being 0. And what is the maximum? The maximum is up to 255. Okay, so how many addresses are there at this step? From 0 to 251, how many addresses are there in total? Isn't it 256 addresses? So, in total, there are 256 addresses. Can I use all of these 256 addresses? Not really. First of all, the address 1.0 is not usable, and 1.255 is also not usable. So why can't they be used? Because in this process, 1.0 is what we call a network address representing a subnet, which will be marked in the routing table on the router in the future. For example, if my router is connected to a device below, let's say it's a switch, and under the switch I have different computers connected, such as 192.168.1.10 and 192.168.210. So if I want to route traffic in the future, do I have to go through this interface? Do I need to specify that I'm going to interface one with my IP address, 192.168.210, and to interface two with my IP address, 192.168.2.11? Is this feasible? It seems too complicated for everyone, especially if we have to write it this way. The global IPv4 address space actually has 4.3 billion addresses. Do we have to write each one like this? Isn't it too cumbersome? Moreover, if a piece of data needs to look up a table of 4.3 billion entries to forward, the transmission speed would be quite slow. So in this case, if they are all like 192.168.2.2, then so I simply write only his network into my routing table to optimize my routing table image. He does the same, using 192.118.10.0 as a substitute for this network segment. Besides this, there's also our broadcast address. Why can't we use this broadcast address? This broadcast address is for when I want to send a broadcast to everyone in this network segment in the future. So now here, I would use the maximum address to occupy the maximum address to convey a message to them. So this also cannot be used. For example, if you tell your friend, hey, I'm going to broadcast something, you're just broadcasting something. But are you the broadcast itself? You're not. So we say this address cannot be used. Therefore, we say network addresses and broadcast addresses cannot be used for devices and interfaces. So how do we calculate a usable address? We can calculate it by raising 2 to the power of the number of available host bits. For example, right here. Hey, how many host bits do we have? If you're not sure how to calculate the host bits, you can take our 32 bits, because our subnet mask is 32 bits. Whether it represents 24, 6, or 16, 8. These are all our network bits. Subtracting the network bits from it gives us our host bits. That means here it equals 8. In the future, when we calculate it, it will be 2 to the power of 8, subtracting 2 from the power of the host bits, because there are 2 addresses that cannot be used, which are our network address and broadcast address. Now the answer we have is that 2 to the power of 8 is 256. Subtracting 2 gives us 254. So in one subnet we can use 254 addresses. Therefore, the range we can use in the future is from 192.168 10.1 to 192.168.10. 254, as for 0 and 255, we cannot use them. Now, let's do a test. For example, we have an IP value of 172.16.10.1 with a 16-bit subnet mask. What are its network address, broadcast address, and the number of usable hosts? First, if we want to calculate this series of numbers, we need to convert it into binary. In this case, our course materials have already calculated it for you, if it corresponds to our subnet mask. This is our network portion. For the network portion, we just copy it down exactly as it is without any changes. As for the host portion, which corresponds to the zeros, if it's our network address, and if we want to in the future. For the network segment, we set all to 0. If we want to calculate our broadcast address, we set all to 1. Finally, we convert it back to decimal to get a result, which equals 172, 16.0.0 and 172, 16, 255, 255. Now, if we calculate all the addresses in this network segment, it is the power of 2 to the number of host bits. So how many host bits are there in total? That is, where the zeros are. The number of zeros depends on how many zeros are in the subnet mask, which is a total of 16. So it's 2 to the power of 16, which equals 65,536. However, we need to subtract 2 addresses. One is our network address, which cannot be used, and the other is the broadcast address, which also cannot be used. So within this, our usable addresses are 65,534. Finally, we calculate its subnet range, starting from 172.16.0011, because 0.0 cannot be used, up to 172.21 to 172.16.255, 254, because 255 cannot be used either. So here we can use the head, but not the tail. Besides these, we also have a situation here where if we have 10.1.112820, what are its network address, broadcast address, and the number of usable addresses? If you manage to figure this out, please leave a comment below my video. Besides these, we also need to know that our IP addresses are divided into public addresses and private addresses. What is a public address? A public address is allocated by IANA, and the allocation method ensures that our IP address is unique within our network. However, this ID is just for you to spend money on its counterpart. Then we have our private addresses. Private addresses are used internally, because if everyone used public addresses, each one would cost money, making it unaffordable for everyone. For example, if a school has a classroom with 30 computers, do I need to buy a public address for each of the 30 computers? In this case, it's unnecessary. We can deploy private addresses for them. In different local area networks, there might be private addresses, and as long as these addresses are unique within the same network, that's sufficient. For example, in my company, my address might be 192 168.1.10, and in your company, you might have a different one. Also have 192.168.110, which is quite normal. Specifically, there is a designated range for these private addresses within the A, B, and C class addresses. For example, Class A. It ranges from 10.0.00 to 10.255 to 55.255. If it's Class B, it ranges from 172.16.0.0 to 172.31.255.255. If it's Class C, it ranges from 192.168.0.0 to 192.168.255.255. These private addresses are often used within companies. If in the future, this is our company's gateway device and this is our computer, we can use these private addresses internally. However, if we want to access the internet in the future, for example, by subscribing to an ISP service, we would then purchase a public IP address. After purchasing this public IP address, when we go online, do we still use the private address to access the internet? Pay attention here. If we all use private addresses to access YouTube, but everyone sees different content. For example, I might watch YouTube to see some beautiful women, while you might watch YouTube to see some handsome men. At this point, YouTube wouldn't know whom to return the data to, because for instance, if our IP addresses are all 192.18.20. For example, if our IP addresses are all 192.168.110, it wouldn't know whom to return the data to. So, in this case, when we want to access the public network in the future, we need to go through a conversion, which means converting our private address to a public address. And this technology is called NAT, Network Address Translation, which is used to switch between private and public addresses. We only need a public address when we want to access the internet. If it's just for internal communication, using a private network is sufficient. Besides these, in our network, there are some special addresses that we should not use. First is the address 255.255.255.255, known as the broadcast address, which is used to send a message to every device on the network. However, its broadcast forwarding is limited by the router's interface. Now, in this context, this is called a broadcast address. That is to say, when this destination address is received as 255.255.255.255, every device in theory should receive it. Of course, it will be subject to a restriction from our router. Besides this, there is also the 0.0.0.0 address. The address, first of all, if it represents that you don't know where you are going in the future, then this address, we can use 0.0.0.0 as a placeholder to represent any network address. Now, if during this process, if I have a device, during the startup process, I haven't obtained an address, but I want to acquire one, then at this point we rely on a protocol in our network called DHCP to request an address. But here's the problem. We don't have an address, so we request one. If I had an address, I wouldn't request it. But when sending this DHCP request, it requires us to carry the original address, but I don't have one. So what do we do then? We just write 0.0.0 to substitute for it. Besides this, we also have 127.0.0.0, which is our loopback address. It can be used for software system testing of TCP/IP packets on our devices. In the early days before Windows 98, many systems actually didn't have TCP/IP. If you wanted this protocol, you had to install it yourself, and after installation, there weren't as many networks as there are now. After you download an app, it asks you if you want to start the machine after installation, congratulating you that it's installed. In the early days, it wouldn't tell you at all. If you wanted to know whether your network was successfully installed, you had to use 127.0 COO to ping this address for a test. So it is used to test whether our TCP/IP installation was successful. Of course, nowadays we rarely use it in our networks because almost all devices now have built-in TCP/IP, so we don't need to configure it ourselves anymore. In addition to these, we also have the 169.254.0.0 address, right? Which is used when our network device is set to DHCP to automatically obtain an IP address. However, If it searches the network and cannot find an available DHCP server, or if the request fails, then the device will temporarily use the 169.254.0.0 subnet. When using the channel IP as temporary communication, it acts as a substitute. However, in this case, you did not successfully apply. You were only temporarily assigned an IP value. So up until 2011, what actually happened? I don't know if everyone has heard, but we've been saying that IPv4 addresses are actually running out and are almost depleted. The last public IPv4 address has been allocated, yet more and more users and devices are connecting to the network. Although we say it's still sufficient for now, because we have divided the private and public networks, I can perform NAT, network address translation. But in the future, I will definitely transition to using IPv6. So what is the difference between the two? Our IPv4 address is 32-bit, while the IPv6 address is 128-bit. Here, we are talking about 2 to the power of 32, which is about 4.3 billion, whereas 128 is 2 to the power of 128. 2 to the power of 128. And here, when we talk about 128, it is also 2 to the power of 128. So sometimes we joke that every grain of sand on Earth could have its own IP address, which shows just how vast the number of IPv6 addresses is. In this process, if we look at IPv4 addresses, their historical types are actually divided into unicast addresses, broadcast addresses, and multicast addresses. And our IPv6, even if divided into unicast addresses, also includes anycast addresses. What are the characteristics of IPv4 addresses? Well, our IPv4 addresses are about to be exhausted. Moreover, there are many design aspects within the header that are unreasonable. If it relies on ARP, it can easily cause broadcast storms. And our IPv6, it has a very large number of addresses. Additionally, its header has been simplified, and we can automatically allocate IPv6 without needing to configure it manually. If anyone wants to learn Huawei certification technology or obtain Huawei certification at the foundational level,